Okay, today we're going to talk about section 9.4, and I think that this, on Math Excel, it'll say which section corresponds to it. It's on, it is posted on the homework assignment. So just to recall a little bit, remember that a chord is a segment with endpoints on a circle. Right? So it's not just a random segment, it actually has to be a segment with um, endpoints on a circle. Okay, so segment PQ is a chord. That's just a reminder. I know that you've just had it recently and gotten a lot of vocabulary, but we're just going to go through a couple of basic things a little bit again. So some basics about chords in a circle. Um, within a circle or in congruent circles, if you have the first statement here says congruent arcs have congruent chords. So according to number 1, if arc AB is congruent to arc CD, then segment AB is congruent to segment CD. And the converse of that is also true if segment AB is congruent to segment CD chord. If chord AB is congruent to chord CD, then arc AB is congruent to arc CD. That's just two statements kind of combined into one. I would not put similar hatch marks on or tick marks on those things. So you can say that segment AB or chord AB is congruent to chord CD, and then arc AB is congruent to arc CD. It does not mean that segment AB is congruent to arc AB. That is definitely not the case. This is a big no-no. You cannot equivocate arc measures with segment lengths. It's not the same thing. So we're going to move on. And another postulate or theorem. Within a circle or within congruent circles, congruent central angles have congruent arcs. So in circle O, that's how we would name that circle, in circle O, if angle AOB is congruent to angle COD, then arc AB is congruent to arc CD. Congruent central angles have congruent arcs. And try to remember from the previous section that the measure of an arc is equal to the measure of the central angle that cuts that arc. So just try to recall that if this is 50 degrees for angle AOB, then arc AB also measures 50 degrees. And then you can also get that angle COD would measure 50 degrees and arc CD would measure 50. Those are not vertical angles, so just be careful. You can have vertical angles inside a circle, but in that particular picture, those are not vertical angles, okay? Within a circle or congruent circles, congruent central angles also have congruent chords. So in circle O, if angle AOB is congruent to angle COD, then chord AB is congruent to chord CD. Remember, you might want to say chord to denote that it means it's in a circle a little bit, because there's really no distinction. There's not a symbol for chord. Okay, so if angle AOB is congruent to angle COD, then chord AB is congruent to chord CD. A segment, remember that a segment length cannot be the same as an angle measure, so just again recall that angle AOB cannot be congruent to to segment AB. That's just a no-no. Angles and do not go with segments, right? They're not even the same thing, so don't equivocate those things a little bit. Okay. All right, so there's a couple of examples that start off kind of easy. So we have circle O congruent to circle P, and we are given that segment, the chord BC, because that's in circle O. Chord BC is congruent to chord DF, and we want to know what could we possibly conclude. Well, there's a couple of things we could conclude based on the information up above. Two things. One thing is that remember that in a circle or congruent circles, and this might be all the way up at the top, or on the previous page, from the previous page, in a circle or congruent circles, congruent arcs have congruent chords, and congruent chords have congruent arcs. So back to this page again. Here we are at the bottom of this page. So we must be able to say that if we have chord BC congruent to chord DF, then that means that we can conclude that arc BC is congruent to arc DF, right? That's because in a circle or congruent circles, congruent chords have congruent arcs, right? They cut off congruent arcs. That's really what we mean by that when we say they have congruent arcs, right? There's another thing that we can conclude also from up here, that if we have, so technically, if we get congruent arcs, right, then we can also say that we have congruent central angles. So after this one, we can also conclude that angle BOC is congruent to angle DPF. So those are just some basic conclusions that we can reach about those circles, right? Because in congruent circles, we can say that congruent arcs, and that was arc BC from and arc DF from above, have congruent central angles, right? Okay. All right, moving on to the next page. And lastly, within a circle or congruent circles, chords, and I'll say this is lastly, but it's not. Chords that are equidistant from the center are congruent. Remember that equidistant means same distance away from, right? Same distance away from. So chords that are equidistant from the center are congruent. So how do we know that these chords are equidistant from the center? How do we know that chord AB and chord CD are equidistant from the center? Well, we notice that we have a little piece drawn from the center perpendicular to chord AB. That's the shortest distance to chord AB. And we also have a segment perpendicular to chord CD. That is also the shortest distance to chord CD. And we see these tick marks telling us that the length of OE is equal to the length of OF. So they are equidistant. They're the same distance away from. Then we can definitely conclude that chord AB is congruent to chord CD. Okay, so if two chords are equidistant from the center, then they are congruent. All right, so now we're going to try this one. Here's what we need to notice. We want to find the value of A. I'm sorry that it's pretty blurry, so let's take a look. There's a congruent mark here and here. This particular piece from P to Q, PQ is equal to 12.5. That's what's known. And then we also know that the distance from the center to segment to chord PR is 9, and we know that the distance from the center to this other chord with a length of A. This is the chord that's a length of A right here, and since it's blurry, I'll try to make it a little more clear. Then that's the length of A. So what we're going to use is the fact that we see two chords. That's segment chord PR is a chord, and we also see this other chord over here with a length of A. And we notice that they are equidistant from the center, right? So A must be equal to 2 times the length of PQ, right? Or you could say that A is equal to PR, and that comes from chords that are equidistant from the center are congruent. That's our justification for that, right? Okay, and how do we find the length of PR? Well, PR has to be equal to twice as big as PQ, which is 2 times 12.5, which should be, excuse me, should be 25. This is supposed to be 12.5, which is 25. So if PR is 25, then that means also that the length of A is 25. There's no unit of measure given, so we'll just leave it at 25. Got it? Okay. All right, now we want to find the value of x. So here's what I notice in this picture. I notice that this piece is 18 and this piece is 18. So how much is the total length of this chord? The length of this chord is 36 units, and the length of this chord is also 36 units, right? So we have two chords in the same circle, and they are congruent to one another, right? So they must be equidistant from the center. So if two chords in a circle are congruent, they must be equidistant from the center. Therefore, remember those three dots mean therefore x is equal to 16, because this length right here is 16, which is the shortest distance from the center to that particular chord that is 36. I know that's not super stressful just yet, but there's going to be a couple others where it gets a little more complicated. So another theorem is that in a circle, a diameter that is perpendicular to a chord bisects the chord and its arc. So where's the diameter in this picture? We're going to notice that the diameter is right here. Chord AB is the diameter because it passes through the center of the circle, and remember that it has endpoints on the circle, right? So it has endpoints on the circle and it passes through the center, okay? And it is shown in this diagram that it is perpendicular to a chord of the circle, and that chord is chord CD, right? And so it bisects the chord and its arc. Then so what we know is we know that segment CE is congruent to segment DE. That's what's being cut in half. But we also know that arc CA is congruent to arc DA. We're bisecting the chord, but we are also bisecting arc CD. We're splitting it in half into two congruent parts right there. Okay? To go along with that, there's a couple of other statements like the converse a little bit or similar statements. If you have a diameter and it bisects the chord and that chord is not a diameter, then it must be perpendicular. So if you have diameter, that's AB, and it bisects a chord, CD, right, then it must be perpendicular to that chord. Remember that that diameter always has to pass through the center of the circle, so look for that dot there. That's kind of a critical deal. Then AB must be perpendicular to CD. So this is just the converse of the previous statement. So you can conclude sometimes that you have a right angle when you didn't necessarily know one. Then you can also conclude bisecting if you do know that you have a right angle. Remember that it has to be passing through the center of the circle. And then the last thing is true. Last thing says that if we have a chord that is the perpendicular bisector of another chord, then it must pass through the center and it must be a diameter. So if it contains the center, if you have a chord that contains the center, that means a diameter, right? Okay, so I noticed looking at this diagram that this chord AB, and I don't know that it passes through the center right now, but chord AB, what I do notice is two things. I notice that it is perpendicular to chord CD, and I also notice that it bisects chord CD. So it's perpendicular and it bisects, so it must contain the center of the circle, so segment AB or chord AB must be a diameter. And sometimes you kind of go, well, I don't know why that even matters. But if you don't know where the center of the circle is, or if you're not sure if something is a center, it's useful. And then if you needed to sketch a center in, you could just add it in a little bit later. Draw in some other stuff that you need to draw in. Okay. All right, let's talk about how we're going to use some of those ideas that were on the previous page. Here we go. So we're going to find each missing length to the nearest tenth. So we will use our calculator and approximate these values. I'm not going to ask you right now to leave these in simplest radical form. But here's what I want you to notice when I look at the first picture for A. What I notice is that LM is a chord, right? And it does not pass through the center. Here's the center. The center is at point K. If I were to, this dashed piece comes from the center and is perpendicular to this chord. So what does it have to do to that chord if it's perpendicular? If it's perpendicular to the chord, so a segment containing, and it can contain a diameter or the radius or whatever, containing the center of a circle that is perpendicular to a chord bisects. That's what we need to know. We need to know that it cuts it in half. Bisects the chord. So that's what we're going to use. So then what we know is we know that we can cut chord LM in half, and we can say that this piece right here from L to where that dash segment hits, and if you need to name it, name it, we would say that that has a length of 7, right? That has a length of 7 from L to here. So then we can do what to figure out the value of R? We should be able to do the Pythagorean Theorem, and we can say 3 squared plus 7 squared equals R squared. That's 9 plus 49 equals R squared. R squared is equal to 58. And don't forget to take the square root of both sides, right? So the square root of 58 is 7.6. And I do believe the direction said to round to the nearest tenth, right? One place behind the decimal. So R, I should put it down below. I always tell you put it down below. So R is approximately 7.6. Got it? All right, let's take a look over here at the next picture for B, and let's talk about what we notice. Okay, because it's kind of a big deal that you pay attention to what all the parts are. So I notice that B is the center of the circle. I also notice that I have a chord right here, and that that chord, if something's being done to that chord, if I have two equal parts, then that chord is being bisected. So I'm going to say that this chord is being bisected, right? All right. Here's what else I notice. I also notice that this is a radius, right? And here's the trick, and something that we forget a lot about a circle is that if we have a circle, we can draw a radius anywhere we want, and it's always going to be the same length. So I could put a radius right next to it that's the same length, or a radius over here that's the same length, or same length, or same length, or whatever. Doesn't really matter, and I don't need to actually keep all of those things, okay? So I can get rid of those. But what I do notice is that there is a radius actually drawn someplace that I need. And since all the radii of a circle are congruent, then this segment BA is also a radius, right? So what's the length of BA? BA has to be also 15 because all the radii of a circle are congruent. Now it looks like we have a segment that is passing through the center of the circle, that would be BC, and it is bisecting a chord, right? So if it's bisecting a chord and passing through the center, then what must be true? It must be perpendicular. If a segment passes through, and I'm just going to make that ugly, through the center, not write that properly, through the center of a circle and is perpendicular, and bisects a chord is really what I meant to say, and bisects a chord, then it is perpendicular. That's the key part that I need right here so that I can find the value of y. Then it is perpendicular to the chord. Okay, so again, it looks like we're probably going to use the Pythagorean theorem all over again. right? So we're going to say, but now we actually know the radius, which in this case, if it's perpendicular to the chord, then this would be the hypotenuse, right? 15 would be the hypotenuse. So I'm going to say y squared plus 11 squared equals 15 squared. So y squared plus 121 equals 225. Y squared is equal to 104. And again, since you're rounding to the nearest tenth, you're just going to take the square root of both sides. And y is approximately 10.2 units. That didn't come out very neatly. 10.2 units, whatever that may be. All right, one more time. Here we go. All right, sometimes you have pictures that look a little funky and you think that you can't do weird things with them, but you can. And what I want you to imagine, and I'm not sure if I can do all this, but we're going to try. This is what I want you to imagine, because this is the tricky part a little bit. When they don't look as strange, then you think that you can't do something with them. But here's what I want you to notice. Again, we have the center of the circle here. We have a chord with a length of 24, and we have a piece that passes through the center, and it's perpendicular to that chord. So what do we say must be done to that chord? So that chord must be being cut in half, right? So that means that this is 12 over here, and this is also 12 here, right? All right, so the interesting piece that you want to keep in mind is, what can you do with this radius right here? You could redraw it someplace else, or if you want, like, I mean, obviously on a video here, I can drag it. So I'm going to drag that radius over here so that I can create a what? A right triangle. But the length is still x, right? So here's my radius here, but my radius remains the same when I move it over here. Got it? So I'm just going to redraw it as a dashed piece so that you can see it that way. And I would put that right here. And that is still going to be what x is. And then we're going to do 5 squared plus 12 squared equals x squared. And if you remember your Pythagorean triples, then you know that x is equal to 13. And we don't have to do all the Pythagorean work for that. But if you forgot, that's okay. You just do the math, and you'll get the 13 as the value of x. All right. The only other thing here on these notes are just some things to remind you, because it's coming up in another section about the definition of all of these things: circle, radius, chord, diameter, secant, and tangent, because those things are coming up again in the next section. So other than that, that's it. That's the end of it. There's nothing more to it, but definitely make sure you understand what each of those terms means and what they look like, and then we'll go forward from there.